My name is Bill Kinney, and this is part 11 of a sequence of videos about multivariable calculus using the computer program Mathematica. What you see here is called a Mathematica notebook, in which we can use Mathematica to do calculations and visualizations, in particular with parametric curves. That's what we've been doing here. And recently we've been using parametric curves to model motion and find the speed and distance traveled for that motion as functions of time. We'll continue that in this video with a more complicated kind of example, something called a Lissajous figure, which you may have seen a physics teacher make for you. We need more complicated commands in Mathematica called NIntegrate and NSolve. Actually, they're not more complicated, they're just new, to help us understand the Lissajous figure that we will see. And here's our example. We've got two trig functions, cosine 5t and sine of 3t, that are defining the motion of an object in the xy plane. I'm not using units in this video, but you could use units. We've got four things to do. Part A says to determine the speed of the object that these equations are describing the motion of as a function of time. Part B says, if possible, determine the distance traveled, dist of t, it's a function of time, starting from time 0, and also ask the question, what can be done if this is not possible? Well, that's kind of a leading question. The hint is it's probably not going to be possible. Part C says make a graph where the motion of the object is shown on the left, so we'll see the actual motion, and on the right you're going to see the graph of the speed and the distance traveled. We'll see the relationship between those things as well. And finally, part D, we'll find one approximate value of time, t, where the speed is minimized. We will estimate the minimum speed and approximate the corresponding point in the curve. So here are the functions. I've got them entered into Mathematica already. I will remind you of the formula for the speed, and I will do it in Leibniz notation here initially just for some variety. It's also maybe a little bit more understandable in Leibniz notation from a certain perspective, which I'm not going to talk about at the moment. There is the speed. It's the square root of the sum of the squares of the derivatives. These are not second derivatives, these are first derivatives squared. I'm going to now go to input mode in Mathematica by putting my cursor down a spot until I see a horizontal line, and go ahead and you type the speed in as a function of t, and here I have to use primes on the functions f and g. Now the speed is in here. You should try to calculate this on your own. There are no trigonometric identities in this case. There's no Pythagorean identity that you can use to really simplify it very much. There it is. That's as simplified as you can get it. The square root of 9 cosine of 3t quantity squared plus 25 sine of 5t quantity squared. It's traditional when you write this by hand to put the 2's, the squares, as exponents of the cos and sine there instead of putting it to the right here. But Mathematica, this is Mathematica's way of doing it, and it's fine. It is going to square those quantities. What about the distance traveled? So that's the speed. What about the distance traveled? In abstract form, we've been talking about how the distance traveled can be calculated as an integral, a definite integral, starting at the starting value of time, which has been 0 for us, and ending at the ending value of time, which is t, of the speed. And it's good to use a different variable here for the integrand. So the integral from 0 to t of speed of tau d tau, that's what this letter is an abstract form representing the distance traveled. We've talked about that. For this particular function then, that will be the square root of 9, I'll write it in the traditional way, cos squared of 3t. Excuse me, I'll use a tau there, plus 25 sine squared of 5 tau. And again, in calculating something like this, you would first calculate the cosine of the 3 tau and then square that result. This is the integral we need to do. However, this integral is not possible to do by what are called elementary functions. If you try to get Mathematica to calculate this antiderivative, it spins its wheels for a while. It's still thinking. It's running. You see the word running up here. It's thinking. It's evidently quite difficult for it. You might scratch your head and wonder why. Well, the reason is there is no elementary formula for an antiderivative of this function. It doesn't mean the antiderivative does not exist. There you see Mathematica basically just gave up there. It didn't know what to do. But that doesn't mean the antiderivative of this function does not exist. It is a continuous function. You can show this integral is well defined no matter what t is. This will be a definite number. You can prove that by theory. So there is a function, dist t, that is representing the distance traveled, and again it's represented abstractly by this. You just can't find a simple formula for it. Instead you have to numerically approximate it, and that's what I'm going to do using NIntegrate. And here's the syntax. Dist of t is going to be NIntegrate of the speed of tau. Tau is going to go from 0 to t. This syntax, rather than an integral symbol that I get from this basic Math Assistant palette, will calculate the distance traveled for any moment in time, for example after 2 pi units of time, by doing numerical integration rather than symbolic integration. The answer after 2 pi units of time is about 24.6. I can plug in pi in here as well, 12.3. I can plug in anything I want. It will do a bunch of integrations, and in fact you can still graph it. And so I've got the code down here that's going to make a graph. This code doesn't run real smoothly, mostly because my machine is not high powered enough. So it's going to be kind of herky-jerky, I think, here. Yeah, it's not real smooth. It's doing lots of integrations. And there's the curve. It's kind of a cool looking curve. That's a Lissajous figure. Physicists often will make this kind of figure with lasers. Okay, I'm trying to pause this. It's kind of slow on me here. Let's close out of that, enter it again, and now I'll just move the cursor this way to get the ending figure after 2 pi units of time. After 2 pi units of time, you're back where you started. This is the figure. We've graphed it. This is the speed and distance traveled. The speed is in red, and the distance traveled is in blue. The speed goes up and down. It speeds up, it slows down. The distance traveled is monotone increasing because the speed is always positive. The speed, the red graph, is the derivative of the blue graph. It's giving you the slopes of the blue graph. The blue graph is found by integrating the red graph. We used NIntegrate to do that, starting at a distance traveled of 0 when time is 0. What is the minimum speed? Well, it looks like this is a low point on the curve right there. When t is around 0.6, we can use NSolve to figure out where the derivative of the speed is 0. In this way, notice I'm using 2 equal signs. I've talked about that before. When you are solving equations in Mathematica, you need 2 equal signs. It spits back some solutions. Not all the solutions, there are actually infinitely many, but these are approximations to the solutions, and this one right here, 0.616831, looks like the one we're after to get the minimum speed. Also 2.52476 would give the minimum speed, but as far as a value of t, one value of t that will give the minimum speed, 0.616831 will work. What is the minimum speed? I can plug it into the speed function, 0.616831. Get a minimum speed of about 0.87. That's how high the graph is there. Again, you could include units on this. And where is the point? I could plug 0.616831 into C to figure out what the point is. Here is the coordinates of the point where the minimum speed occurs. I could now go back and copy and paste this code to also plot that point in the picture inside this list plot, negative 0.998351, comma 0.961139. This point up in the upper left there, that's a point where the minimum speed occurs. That should be a corner, and that makes sense. I say corner loosely. Of course, it's not an actual corner. It's a place where the curve is moving in a tight curve. It should make some intuitive sense that the speed is minimized there. Alright, here's your exercise. It's similar, not much different. F of t is cosine 5t, g of t is sine 4t. Basically, you're doing the exact same type of things. The speed is this. The distance traveled in abstract form is this. We again use NIntegrate to go ahead and calculate the distance traveled. It's a different distance traveled this time after 2 pi units. It's further. Here's the graph. It's a similar graph, though not exactly the same. It's another Lissajous figure that again ends back where we started after 2 pi units of time. Here are the speed and distance traveled. And it turns out using NSolve you can figure out the critical points of speed. One where it's minimized is at about 1.2. Yes, this one right here, 1.23422. And you can approximate the minimum speed to be about 1.05 and the corresponding point to be at about 0.99 comma negative 0.97. And you can plot that in the graph as well. That's the end of this video.